welcome to the Carr Center for Human Rights Policy and the Sustainability Science Program study group. And we're pleased to have Professor Tom Gleeson with us, who is an assistant professor at McGill University in Canada and is also a CIFAR fellow and is here for a CIFAR meeting. And we're delighted to have him because groundwater and the availability of groundwater is really a pressing issue. And with a PhD in civil engineering and a real interest in how to take basic science and apply that to real-world problems around sustainability and the environment and water resource management, has developed a new tool that's been written up in Nature that's called the Global Water Footprint. So I think we're really eager to hear about your work, so welcome.
Thank you. Thanks for me. I'm really excited to be here. The title for today's talk is From Global Groundwater Depletion to the Sustainable Use of Groundwater Systems. And this is work that I've been doing for the last couple of years at McGill in collaboration with two other groups. One other group from Utrecht University in the Netherlands, and they are global hydrologic modelers, so they study and model how water flows through in all the different continents of the world. And another professor at Heidelberg University who's been really trying to compile data with me and write about groundwater depletion. So I wanted to start off today's talk with my existential question, what my motivation for the world, in the world of research. And this is the question that keeps me going, and it's how can a hydrogeologist meaningfully contribute to water sustainability in a changing world? And I approach that question in kind of 4 different ways. And I just wanted to say from the very start that I'm really open to any discussions. This is a really informal talk. So just interrupt or put up your hand or whatever. And I'm really excited to be here because I'm more and more interested in moving my research towards sort of policy relevant directions. And so I wanted to come and show you some of the scientific work and some of the policy relevant work I've been doing and sort of get feedback from you as well and have hopefully a nice discussion about how to continue to move in that direction. And so this is how I orient my research from the science policy spectrum with, have here the mind the gap sign from the London Tube Underground, where we have to mind this gap between science and policy, or that's what some people think. And I understand that there's a lot of scientists think there's a linear trajectory between good science and good policy, and that's a fraught idea, and I'm not trying to propose that idea at all, but I just orient my sort of 4 fields of research along this kind of spectrum. And so the first is to really examine biophysical systems, so how hydrogeologic systems work, and document that, and document how humans are starting to really impact those hydrologic systems around the world, and then work towards developing a sustainability science for groundwater. I've been working on that for the last couple of years, and I'm going to talk about that today, and eventually and into the future, and that's why I'm excited to be here, start to contribute more significantly towards policy and management in groundwater and other fields. So that's my motivation. And what I plan to talk about today is, since no one in this room specifically introduced themselves as a hydrogeologist, that I'd try to convince you first that groundwater is important and why we should care about groundwater, and then tell you a little bit about what groundwater really is, starting off with a childhood experience you might have had, and talk about what groundwater depletion is, and then talk about what footprints are. So I'm going to be talking about groundwater footprints, and I want to introduce the idea of a footprint and what it is to give you some background as to what a groundwater footprint might be. Then I'm going to talk about these groundwater footprints for the whole world and what we've calculated recently, and then delve into a couple more specific areas. So it's always nice to see these global maps, but it really, when we talk about policy and real discussions about what we can do, it's always grounded in real regions. And so I want to talk about some aquifers and groundwater management and groundwater depletion in India, the United States, and China. And then I want to talk quite broadly about the causes of groundwater depletion, and hopefully end on a little bit more positive note. David Suzuki is a famous environmentalist in Canada, and all his speeches and talks are always like 45 minutes of dour and depressing, and then 5 minutes of of good uplifting stuff at the end, so I'll try to do that as well. Maybe we'll even get a little bit more optimistic earlier on, we'll see. So some of the long-term solutions that I'll talk about are backcasting. This is another way of looking into the future. Adaptive participatory governance, this groundwater footprint, how it can be used, and strengthened groundwater policy. So these are my 4 reasons why I think we should care about groundwater. The first is it's the primary drinking water source for about 2 billion people around the world. So a quarter of the world's population drink groundwater every day. And often these are in rural areas because centralized water sources aren't available. And so, and with the amazing and valuable thing about groundwater in many ways is that it's very predictable. It flows a lot slower than surface water, so it doesn't vary seasonally nearly as much as surface water. And when I mean surface water, I mean lakes and rivers and things like that. And so it's much more predictable. People know that they can get it, and it's often cleaner than surface water. Surface water is easy to contaminate, and groundwater naturally remediates and filters some contaminants. So it's just, there's obviously exceptions to every rule, but just in general, it's a very stable and clean water source. And it does cost often some money to access through drilling a well, but in a lot of areas around the world, it can be accessed with fairly limited means. There's very cheap and affordable drill technologies for drilling wells. The second, and these aren't in any specific order, but this is just the order that I think of them in. The second major reason why I think we should all care about groundwater is that it plays a central role in irrigated agriculture. So 90% of the water use around the world is for irrigation. And here's a photo of a pivot irrigation and in a relatively arid area. And 40% of that irrigated water is groundwater. So groundwater is a crucial source in many regions of the world. And again, it's valuable in the same way that it's valuable as a drinking water source because of its consistency and its predictability. It's available almost everywhere or quite consistently. You can be far away from a river and not have a surface water source, but you can drill a well and usually obtain groundwater. It's also really important for many ecosystems. So in the summer or in the dry season around the world when there's very little rain, most of the water in a river actually is coming from groundwater. So all the ecosystems that depend on river water or wetlands and other water depend on groundwater during the dry season. So there's a lot of ecosystem dependency on groundwater. The last, and maybe the biggest reason to really care about groundwater as we move forward is that 99% or over 99% of the fresh, unfrozen water on planet Earth is groundwater. That's an amazing fact. I always tell, when I meet a grandmother or somebody in the shopping mall and they're, what do you do? I study groundwater, and this is the amazing fact about it. So what that means is that it's this huge reservoir that's very stable and predictable, and it could be a huge reservoir that we could use into the future as a buffer for different uncertainties that we face in the future, whether they be climatic, economic, social, or political, if we manage it properly. So those are the 4 reasons that I think groundwater is really important and should be thought about. So I've said groundwater probably about 15 times already, so I wanted to just make it really clear in people's mind what we're talking about when we talk about groundwater. And this is the simplest way that I can explain groundwater. And it's if everyone remembers being at the beach when you're a little kid and you dig a hole, and that hole fills with water. Well, that's groundwater. It could be saline water or slightly salty water because if it's right by the ocean. But groundwater is the water beneath our feet that is stored in the cracks of rocks or between the grains of the sand in the beach. So there's not some magical cavern in most places of the world. It's just between little rocks, fractures in rocks, or between the little grains of sand, and that's what groundwater is. And unfortunately, groundwater isn't very photogenic. It's actually invisible. So for people who need a visual inspiration for what to think about for the environment, or things to protect, groundwater doesn't have a lot to say for itself. But here are some photos of groundwater, just to give you a little bit more idea of what we're talking about. On the top left is a photo of a flowing well in Egypt, a really important aquifer called the Nubian Aquifer in northeastern Africa. On the top right is a photo of a well drilling operation, and so that's how you get water out of the ground. You drill a well, and then the bottom photos are springs where groundwater flows out of the subsurface and starts a river or a creek, and these are natural outflows of groundwater. So groundwater is part of the hydrologic cycle, or the water cycle of the Earth. It's intimately connected with surface water. So with lakes and wetlands, they can either flow in and out of groundwater, and it's important to know that they're directly connected and therefore should be managed together. One big difference between groundwater and these surface water sources is what's called the residence time, or how long water stays in these different reservoirs. For lakes and rivers, this can be on the order of weeks or sometimes years, whereas groundwater can stay underground for centuries or even millennia in some cases. So there's a visualization of groundwater flowing in the subsurface, and you can see that there's some very long flow paths that take a very long time. And so when we're thinking about how to manage groundwater, we have to start thinking on those very long time scales, because this is the time scales that it's operating on. And I'll talk about that later in the talk when we talk about some tools that we can manage groundwater with. This is a graphic to really hit home the differences between groundwater and other water sources and water reservoirs on the planet. So on the left-hand side is the flux. So this is how much the volume of water coming in or out of these reservoirs. So groundwater has a very small flux. So there's very little water coming in or out of aquifers, which hold groundwater, but it has a huge storage. And this is what we were talking about before. 99% of the fresh, unfrozen water on the planet is groundwater. And a very long residence time. And so it's this huge reservoir that can buffer future change. Whereas surface water, there's a lot of water coming in and out of surface water systems, but very little stored. So it's a less stable and more vulnerable water source to change. And soil water, this is what's often talked about as green water. This is the water that plants use to grow. Has even larger fluxes in and out, but a smaller storage. So these are the fundamental differences between groundwater and these other water sources, and why it's important and different and can be thought of in different ways. So the second thing that I wanted to introduce you to after introducing you to groundwater is introduce you to what is groundwater depletion. So what does that mean? And the simplest way to define groundwater depletion is the permanent loss of groundwater stored in aquifers. So groundwater flows in and out of aquifers, and this is a natural process, and that this always occurs. But depletion is when we're actually losing water that was stored in there sometimes over very long time scales. So on this diagram here, we have a natural flow system on the top, and this natural flow system, groundwater flows in, and this is called recharge, and groundwater flows out, and that's called discharge. And then on the bottom diagram, this is a groundwater system after there's been some development. And in the development means for groundwater that we start pumping wells. So we drill wells and start pumping them. And so on this diagram, this E is extraction or removal of groundwater. And what happens when we extract groundwater is that the water table, which is the level of water in the subsurface, draws down. And that leads to a number of different changes. It can affect how much water goes to rivers in the summer or lakes. So this is the groundwater discharge. And this affects ecosystems and other things that are dependent on these lakes and rivers in the summertime. It can also increase the rate of water going into the aquifer. This is called groundwater recharge. This is the big arrow on the top left. And we can also, what often happens is that we irrigate crops. So I said that most of the water around the groundwater used around the world is for irrigation. So when we irrigate crops and grow food with groundwater, we increase the rate of evaporation and transpiration. So we lose more groundwater through those crops, and that can lead to that leads to this depletion, which is this permanent loss of groundwater from aquifers. So what does groundwater depletion really look like? I said a couple minutes ago that groundwater is invisible, so it's kind of hard to see, hard to really care and imagine what it really looks like. So I wanted to put together a couple photos of what the manifestations of groundwater depletion. The first manifestation of groundwater depletion is this lowering of the water level, or the water table. And so this can lead to dried up wells or less water available in these wells. The second manifestation of groundwater depletion is the loss of streams and wetlands. So this is an amazing map of Kansas over from 1961 to 1994. And what you see is that there's a number of springs. This is a map of the rivers and streams in Kansas in 1961 that actually just dried up and no longer flowed because the water table in the aquifer, this is the High Plains or Ogallala Aquifer, that's talked about a lot in the United States, and I'll talk about that a little bit later. The water table lowered, and it stopped the flow of groundwater to these these streams, and caused these streams to dry up. And that's obviously all the water dependent ecology in these streams also were affected or died. The third, sometimes really important manifestation of groundwater depletion is subsidence. So when you pump or remove water from an aquifer, the land surface actually lowers. And in some areas of the world, this happens by feet or tens of feet or even tens of meters. So this photo here is in the Central Valley in California. And along this telephone pole, we are charting where the land surface was at different times. And this is it's really quite incredible. There's been tens of meters of, and this is actually this was taken in 1977, more than 30 years ago, and the land surface has dropped even further since this photo was taken. And you can imagine how this could easily really impact a lot of infrastructure, any kind of piping or this electrical infrastructure. And this is a huge problem. It's probably most talked about in Mexico City, but in a number of cities around the world, there's significant subsidence from groundwater depletion that affects infrastructure and how we move through the city in many ways. The third manifestation, the fourth manifestation of groundwater depletion is social and economic problems. Here is a protest in India over groundwater depletion and contamination by Coca-Cola. This is in southern India, but there's been a number of pretty significant protests in northern India as well over groundwater-related issues. So these are sort of the manifestations of groundwater depletion, and just recently, it's that for the first time, we've actually mapped groundwater depletion over the whole world for the first time. So this was a paper that came out a couple years ago in 2009. And this is a map of groundwater depletion. And I've remade this map from the original publication so that we can see the depletion around the world as mountains. So the black mountains in this map that stick out from the rest of the continents show you the rates of where groundwater is being depleted. And so you see that the areas with the most significant groundwater depletion around the world are in the Western United States and Mexico, in Iran, Saudi Arabia, and India, both northern and southern India, and in northern China. And so this map was created by modeling one of these global hydrologic models, and taking the recharge, so this is the rate of water going into aquifers, and subtracting the rate of groundwater use. So this is the difference between the inflow of aquifers and the rate of use. And this is a simplified version for how to calculate groundwater depletion.
What was the time frame?
So this is the groundwater usage data is from around year 2000 for most of the regions, but it is really a patchwork of different sources of information for groundwater usage in different countries. So it will be different for slightly different countries.
Is this a rate at a point in time, or a rate that averages? Over
so this is a long-term average. So both for the inflow and the usage. So this is you can think of this as like this is how much is being depleted every year from these places on average. So since this first estimate came out, there was a few other estimates using different models to estimate groundwater depletion around the world. So here's a graph of these different estimates. And you can see on the left axis is the depletion volume. So this is the total depletion rather than the average depletion every year. So this is since 1950, how many cubic kilometers of groundwater have we lost around the world from groundwater? So you can see that there's some really high estimates of upwards of 20,000 square kilometers of groundwater that's been lost. And it's really hard for policy people, or quite frankly, even for hydrologic scientists, to really visualize what a cubic kilometer is, or thousands of cubic kilometers. So the next thing that I'm going to show you is the groundwater footprint, which I think is an easier way of visualizing the same problem with these same data. What's interesting is that this groundwater depletion, we all know that matter and water is not created or destroyed. So a good question is, where is this groundwater going to then? And it's actually going to the ocean. So you can see on the right-hand axis is how this groundwater depletion is leading to sea level rise. So not only are we depleting the aquifers on the continents and creating a host of problems from that, but we're also increasing the rate of sea level rise and causing or exacerbating potentially problems in coastal regions. So we have sort of a double-edged sword here.
Could you explain a little bit more about how that water balance calculation is done? Because it seems to me reasonably simplistic to assume that just because groundwater is used in one place, I'd be interested in understanding how that was calculated, because obviously there are a whole lot of other elements in the hydrological cycle that might account for that overall water balance, A, and B, we haven't seen that level of sea level rise.
Yes, this is just a part of the sea level rise, and actually the sea level rise has largely been buffered by our habit of building dams. So there's quite a few papers that have documented how sea level rise would be more significant dam building to some extent has slowed down over the last couple decades around the world, but we are still building dams, and that water that's stored in dams is not being then taken to the sea, at least immediately, and that's lowering the rate of sea level rise. But as our habit of at least making really large dams around the world is starting to decrease, there's some thought out there that that sea level rise and the importance of groundwater depletion in sea level rise will become more important over the next, say, 2 to 3 decades. And the other part of your question about, I'll just go back to the last slide then to just talk about some of the data sources for these calculations. And so the recharge estimate, the inflow estimate, is derived from a global hydrologic model that starts with the outputs of a climate model and models all the physical processes of water flow at the Earth's surface, like infiltration, evaporation, stream flow, and is calibrated or compared to stream flow records around the world. And so, it is an interesting question about where or how some of these, how this groundwater depletion gets to the ocean. So a really cool example is in the High Plains aquifer in the central United States. It's a very arid region, and this groundwater depletion causes, the groundwater is used and depleted, and this groundwater use is for irrigation, and that irrigation causes increased evapotranspiration, and that has caused increased vapor flux in the atmosphere, and that vapor is actually transported, a recent study just came out and shown, to mostly around the area of Illinois, which is a more humid region. So what we're doing here in the United States is we're, whether we like it or not, we're transporting we're taking groundwater from a relatively dry region and transporting it via the wind currents to a relatively humid area that doesn't need water. That's kind of what we're doing. And then eventually that reaches into the Great Lakes and into the ocean.
Yeah, so, sorry, can I ask? Sorry.
Yeah, please.
So just in terms of understanding that graph then, what I was interested in is the extent to which it was a reasonably simplistic link between if you took this much groundwater out of the system and it made its way into the sea, this is volumetrically, quantitatively the likely impact.
Right.
Or the extent to which that expression had been modified by these other, a more sophisticated calculation of the likely flow impacts in the, increased evapotranspiration and what that means from an atmospheric process of filtration and blah, blah. So am I right then that the graph is a more straightforward, simplistic link? Or are you saying that it incorporates some of those other?
The estimates of depletion do incorporate these different elements and processes of the hydrologic processes.
Yeah.
One thing that most of these estimates don't do a really good job of is taking into account the dynamic nature of aquifer response to extraction. So when aquifers and groundwater are modeled in very simplistic ways in these global hydrologic models, where they're just considered to be stores that don't dynamically respond to extraction, so they don't increase or decrease the discharge, as I said before, in these global models. So that's kind of a limitation, and that's kind of where we're evolving to, hopefully, in these kind of large-scale hydrologic models, but we're not there yet. But most of the land surface hydrologic processes are incorporated in these models. And then you're right, that it is a simplistic kind of volumetric transfer in calculating the potential impact of that on sea level rise. Yeah.
Sorry.
No, it's great. It's an open discussion. Yeah.
It was just with the next slide with the graph.
Yeah.
Because you have 4 different colors, so I just want to understand, and definitely blue one is higher, so we just or maybe I'm missing it now. Missing it translation.
Sure. No.
Because you have 4 different.
Yeah. So the first estimate that I showed you in that last map is this solid red line here, and this was derived by the process that I just described, a global hydrologic model, subtracting groundwater use around the world. And the green line there was derived from specific direct observations of groundwater depletion. So it's kind of a smaller, probably more conservative estimate of groundwater depletion. And the blue line, which kind of goes a little bit off into outer space, is probably an overestimate, and it was derived from a global hydrologic model again, but they made an oversimplification of how groundwater works. They considered that groundwater is basically an infinite reservoir. There's always going to be groundwater available, and there's always going to be enough available. When we know that that's not true in a number of places of the world. So what that means is that they overestimated groundwater use and therefore groundwater depletion. All these papers have come out in the last 2 years, so it's really an active area of research, and there's not a lot of resolution on which one is best. But scientists generally like to, if there's 3 lines, they like to go with the middle one, whether it's right or not. It just looks best on the graph. So maybe that's what will happen, but I don't know. Yeah.
Can I ask a question just about virtual watering? So actually when you have, so going back to Shannon's question about how it's calculated, does the amount of water that's actually leaves the system in the form of crops, is that accounted for?
For sure, yeah. So to the extent that it's accounted for in these national water use inventories. But this analysis isn't really taking into account where that virtual water goes. What we're looking at is how the use is affecting specific areas. It's a whole other, an important and interesting analysis to do, but to answer the type of question like, so you're growing wheat and beef or wheat for beef in the high plains in Kansas, so where is that virtual water going? Who's consuming it? So the last part of the introduction, this is a kind of lengthy introduction, but there's some good stuff in it, so is what is a footprint? There's 2 types of footprint that I want to describe, and they're quite different actually. The ecological footprint was derived in the early 1990s at UBC, and I was actually at UBC when I started thinking about this stuff, and so I was inspired by some of the work that had been done there. And the ecological footprint is an area-based method that measures the demand that we use broadly over Earth's ecosystems. And by calculating the area or the equivalent area of a resource use and consumption, you can make all kinds of really interesting assessments, like how many Earths we're using in resources. These are obviously very kind of crude calculations, but they're kind of eye-opening. So what is generally calculated now is that we're using about 1.4 Earths worth of stuff all the time. So we're over our carrying capacity. The water footprint is quite different. The water footprint is based on volumes. So it's the volume of water needed to produce a good or service. And I see some people drinking coffee or tea. I always like using the coffee example. That a lot of people know this, but it takes 140 liters about of water to produce your cup of coffee, even though it's 250 milliliters. And the question is whether that's really important or not from a water availability question, from a water availability perspective. So in some regions of the world, like Costa Rica, coffee is grown in a very humid region. 140 liters may not be all that important, or I should say that the impact of that may not be all that significant on the hydrologic or environmental cycles and systems. Whereas coffee is also grown in arid regions like parts of Ethiopia, as where it's originally found. And the impact of that 140 liters might be much more significant from a hydrologic or environmental perspective. So I tried to take that into account when I developed this new idea about the groundwater footprint to not only look at the water use and consumption, but how that affects the environment. So the groundwater footprint is really more inspired by the ecological footprint idea. So it's, I'll just read this definition. The groundwater footprint is the area required to sustain groundwater use and groundwater-dependent ecosystem services in a region of interest. So it's the area needed to maintain a sustainable water use in this region. And I don't want to get too bogged down in the nitty-gritty details, but I wanted to give you some idea of how we do this calculation. The variables that we use are shown on this graph here, and you can see that, or sorry, on this graphic. And the variables are recharge, which is R. This is the rate of groundwater going into an aquifer. And then that water obviously comes out, as I mentioned before, and this is called groundwater discharge. This is the groundwater that flows to rivers or creeks or wetlands. And we're saying that we need to take at least part of that groundwater discharge and allocate it for the environment. This is called environmental flows or ecological flows, ecosystem flows. There's 10 different names, but and they have slightly different meanings to slightly different people, but they all kind of are under the umbrella of how much water we need for ecosystems. And so, and that's a very active debate right now as well. There's a lot of discussion about how we can set these environmental standards for stream flows. And the last two variables that are important are the consumption, which is C in this. So this is the rate of extraction of groundwater, and the area of the aquifer. And so this is we've calculated this for aquifers. So these are the geologic regions of groundwater, but it can also be done for at a variety of different scales. So these are the data sources that we used in the first initial calculations of the groundwater footprint for the large aquifers around the world. So on the top left is the estimate of recharge from a global hydrologic model. On the top right is the consumption of groundwater from this patchwork of different national databases of groundwater use, national and subnational databases. And then on the bottom right is the environmental flows. And we did this kind of, I'll say quite simplistically for this global analysis, by setting a fraction of recharge for these environmental flows. But we really just wanted to develop this method of the groundwater footprint and show how it can be used. And then water managers in different parts of the world or even globally can set, as we evolve and start to set environmental water flows, you can use this method and directly substitute in whatever environmental flow you think is reasonable into these calculations. So we set the environmental flow of groundwater as the stream flow that's exceeded 90% of the time. So this is the stream flow that is mostly derived from groundwater during these dry seasons. That was what we set for environmental flows for in this analysis. So this is the product of this calculation of groundwater footprints for different aquifers around the world. And there's a lot going on this map, so I'll sort of walk you through it slowly. On the main map, the aquifers of the world, you can see that we just picked the large aquifers of the world. So there are a number of other small aquifers that are important for some regions, but we had to pick a certain scale of analysis, so that's the first thing to know. The colors on this global map of reds to blue show the groundwater stress in these regions. And so we calculate the area of the groundwater footprint for each of these specific aquifers, and then divide that area by the actual aquifer area. So, and this ratio of GF, groundwater footprint, to AA, aquifer area, is an indicator of groundwater stress. So if this ratio of GF to AA is less than 1, the groundwater use, at least at the scale of the aquifer, is largely sustainable in our analysis, whereas increasing numbers of this ratio are increasingly stressed aquifers. And so these red and oranges on this map are the aquifers that are the most stressed around the world. And what you can see then in the bottom are kind of highlights of a few of the aquifers with very large groundwater footprints, where the black area on these maps are the aquifer, the specific aquifer areas. So going from left to right, this is an aquifer in western Mexico, and the High Plains or the Ogallala Aquifer in the United States, the northern Arabian Peninsula in Saudi Arabia, the Persian Aquifer in Iran, the Upper Ganges Aquifer in northern India, and the North China Plain. And on each of these, the aquifer area is in black, and the groundwater footprint is this blue area. And it's at the exact same scale as this global map. So you can see these groundwater footprints are absolutely gigantic in comparison to the actual aquifer area, and if you just plot it on the map, the global map. So this is the degree of unsustainability you can think about in their groundwater use. But the other important point to take away from this map is shown in the graph in the upper right-hand corner, where you see it's a histogram, so this is a frequency of aquifers, and you can see that most aquifers have a very low ratio of groundwater footprint to aquifer area. So with that, and you can see this on the map as well. There's a lot of blue aquifers on this map. So the overall message from this figure is that there are a number of aquifers in the world. Many of them are being used sustainably. There are a few aquifers that are being exploited very extensively. And unfortunately, those few aquifers that are being overused are in regions that are critical for agriculture. And there's no accident there either. These aquifers are being exploited by agriculture, and they're in regions that are important to agriculture in the United States and in India and China. And I'm going to talk about some examples of that.
Excuse me, these numbers, that you indicate 7.9 or 54.2, do they in any manner show that these countries are the most water stressed? Because China, for example, is one of the most water stressed countries, but I don't see anything, the data on top of that, because...
Yeah, so it does show the groundwater stress in these regions. And that, depending on how water is managed, that could or could not be absolute water stress. It could be different. But there are a number of aquifers in China that are kind of smaller ones are red and orange, and then the major aquifer that I'll talk a little bit about that's quite well known for groundwater depletion is the North China Plain, and that's kind of a yellowy color on this map. Maybe it doesn't show it very well. So here's a graphic that doesn't show up very well on this screen, which is fine.
Couldn't figure out how to turn those front lights
of where the people live that are affected by groundwater depletion. So if you take the aquifers that have a groundwater footprint to aquifer area ratio of greater to 1, we can split the aquifers of the world into aquifers that are stressed and less stressed in a very simplistic way. And what this shows is that there are about 1.7 billion people living in places where aquifers are stressed, and most of these people live in northern India and northern China. We can also do another analysis of where groundwater could be used to sustainably grow more food. And so here's an analysis where the green colors show places where there is groundwater that is less stressed and where there is potential for new calories. So this is based on another paper of potential agricultural production by Jonathan Foley's group at University of Minnesota that came out in Nature last year. And they have these global agricultural models, and they're calculating the potential for new calories around the world. And so what we've done here is compared that to where we could sustainably use groundwater. So the red areas are regions that have potential for new calories and but are under groundwater stress, and the green areas have potential for new calories but are not stressed, or not, the groundwater footprint shows that they're not stressed. And in the future, climate change could also impact these some of these aquifers. This is estimates of how groundwater recharge could change. And so the blue areas on this map show aquifers that could have that have depletion and could have more recharge, whereas the yellow and red regions show areas that will have or predicted to have decreased recharge, and that could exacerbate groundwater depletion problems. So I want to quickly talk about a few different regions of the world, just to give you a flavor of what goes on actually in the ground, at the ground level in some of these aquifers. The first aquifer is here in the United States, the High Plains Aquifer. And here, an overview of the High Plains Aquifer. Almost 30% of the irrigated area in the United States is in the High Plains Aquifer. But the water availability in the High Plains Aquifer is very different from the north to south. It rains a lot more in the north, and is quite arid in the south, in Texas and in southern Kansas. And it's very important both economically and for food production in the United States. The bad news about the High Plains Aquifer is that there's significant groundwater depletion that's occurred over the last 50 years, largely, and that's affecting large areas within the High Plains Aquifer. So this is a map on the left of the High Plains Aquifer and showing groundwater depletion levels. So this is the actual drop or decline of the water table in feet. You can see that there's been drops of 20 to 40 feet over entire regions of this aquifer. And on the right is a graphic of the rate of decline. You can just see it's a systematic decrease in the water level in Kansas and Texas, but there's not nearly a significant decline in Nebraska, for example, because it rains more there. I want to spend a little bit more time talking about the aquifers in northern India. The Upper Ganges aquifer has the largest groundwater footprint of any aquifer around the world. And I'm just starting to work with the UN FAO organization in India to do more detailed calculations of the groundwater footprint in this region, but I'll just show you some initial calculations of the groundwater footprint. Groundwater is extremely important in northern India. 1 billion people live on top of this aquifer in northern India and Pakistan. And there's been a transformation from previous water use from surface water irrigation to, in the last 30 years, as part of the Green Revolution, millions of largely private water wells have been drilled and are tapping and using the groundwater, and a large groundwater economy has developed here, and is partially influenced, interestingly enough, by the highly subsidized electricity. So on the bottom right here is a map of the estimated 20 to 30 million individual wells in India. And this is very different than the United States, where there's a much smaller number of wells. So any solution or possible policy or management scenario that you think of for India and other countries that have these incredible number of wells has to take into account just that basic fact of how many wells there are and how distributed they are. India has also had the greatest rate of increase of agricultural groundwater use over the last 30 years. And this has led to serious depletion in northern India especially. This is a map of groundwater depletion from space in northern India. So this is a NASA satellite called GRACE. It's a gravity satellite. And by measuring the differences in gravity over a 10-year period, you can see that, or you can show that water has actually been lost from the aquifers in northern India. And we can see that on the map here, it's equivalent loss of upwards of 10 centimeters over this entire region. And so in some areas it will be much, much larger on the order of meters. And this is over a broad hundreds of square kilometers in northern India. We did a very approximate and crude calculation of how you could use the groundwater footprint to calculate scenarios of groundwater use in some region. We use this region of northern India as an example in this paper we just published. And the reason we did that is because the Upper Ganges aquifer has this incredibly large groundwater footprint, the largest in the world, whereas the aquifer right next door, downstream, the Lower Ganges aquifer has much higher rainfall rates, much higher recharge rates, and lower groundwater consumption. So we just wanted to play a hypothetical game of what would happen if we would transfer groundwater use, not actually transfer the actual groundwater, but just transfer the groundwater use from this western part of northern India to the eastern part, or part of it. And how would that affect, could these systems be sustainable or not? Obviously there are a whole raft of other very much more complex scenarios about why food is grown there politically, socially, economically. This is just, I just want to make it very clear that this is just a water budget question at this point right now, and this is the calculation we're just doing. And this, the graph on the right shows the result, and this is the ratio of the groundwater footprint to aquifer area again. And you can see the Upper Ganges, as we transfer water from water usage from the Upper Ganges to the Lower Ganges, the groundwater footprint of the Upper Ganges, this blue line, decreases. The the groundwater footprint for the Lower Ganges does not increase as rapidly because of these high recharge rates. But the total, as seen in green, of the groundwater footprint for these two regions remains above 1, which means that overall, no matter how much water, if you transfer all the water usage, the entire system will still not be sustainable. This is just a hypothetical scenario, but it just illustrates how the groundwater footprint could be used to think about groundwater usage and how sustainable it could be in different regions. I'll just speak briefly about the North China Plain. It's another incredible story of groundwater depletion. There's been a shift here from primarily rain-fed irrigation to double cropping of wheat largely, but other crops as well. And this has led to significant groundwater depletion. This is a cross-section of this aquifer, and you can see the water level in different years, starting in 1964 to 1998, and across this broad region of hundreds of square kilometers, upwards of 30 meters of groundwater has been lost and depleted. So this is a gigantic volume of groundwater that's been depleted from this area. And what's interesting is that this has been a known problem for quite a while, and farmers have known, when the farmer's well runs dry, they know that they've run out of groundwater, and they've consistently been drilling new wells over these decades. And they tried to increase the irrigation efficiency in the 1970s, but that actually didn't lead to any significant decreases in the groundwater depletion, because the problem is that the irrigation water is actually just all being lost to evapotranspiration. So even though they increase the irrigation efficiency, they're still losing so much water of this groundwater that's used as irrigation water to evapotranspiration that the rates of aquifer decline didn't go down. So
when you say efficiency, like in terms of using micro irrigation or drip irrigation?
yeah, a whole raft of different things, but all of it didn't matter because it's how much water they're using to grow crops, which is being lost to evapotranspiration.
Because they're growing more crops.
That's right.
That's going on.
That's right. And so this has led to suggestions that the only way to really decrease groundwater, or halt or stop or slow down groundwater depletion in this region is actually to decrease the irrigated area, not the irrigation efficiency. So, but that's a solution that is very controversial and it's very political. It's a lot easier to sell increasing irrigation efficiency than.
So can I ask a follow-up question on that? So if they had maintained the same level of crop production, but introduced the micro irrigation, drip irrigation efficient solutions, would that have, do you think that would have led to any change?
It depends if they would have stayed with single, they did shift from a rain-fed crop, single rain-fed crop generally, to double cropping per year. From my understanding is that they couldn't really have done that without irrigation water. And as they did that, the evapotranspiration increased dramatically.
So-
Yeah.
No,
Less
yeah.
efficient irrigation, I guess I'm curious about, obviously most went up through evapotranspiration, but was the less efficient irrigation process also allowing for recharge to the groundwater system?
That's right. Yeah, but
so it's just the balance of how much you're pumping out through the leaves versus how inefficient you are, and it's either.
yeah, and you do need a certain all irrigation
Yeah.
people know you need a certain amount of inefficiency, as it's called, in order to dilute salts.
I think that's where you were kind of going.
Right.
John.
Right. So, and another case that's been talked about is in the High Plains aquifer, where increased in the United States increased irrigation efficiency actually just led to numerous farmers increasing their irrigated area, which led to more significant groundwater depletion.
I was actually just thinking of the India example.
Right. Okay.
And so if you contrast where it seems like the theory is that so there's subsidized electricity and people are pumping all this groundwater out, and so if you could actually encourage people to both pump less but also move from flood irrigation to drip irrigation, you could reduce groundwater consumption, so the theory goes. But this is an interesting example of a different solution then leads to more crop production.
It's like these counterintuitive irrigation outcomes that are really interesting. Yeah.
I think the use of the term efficiency can be misleading, because if it's inefficient yet it's actually something you're still capturing within the system through maintaining or increased recharge, well, that's potentially not necessarily such a bad thing unless you're mobilising unpleasant chemicals with that. But we use these terms efficiency, and then that drives a particular outcome, and we don't. It's the same as the challenge of the whole linking between groundwater and surface water, and the extent to which pulling on one thread or the other thread and making this point in place. I think there's an issue with terminology and how we capture and explain the whole cycle and what that means.
Yeah, I agree. I mean, the word efficiency is a very engineering word. I'm obviously coming from an engineering department, so I'm not going to baldly criticize engineers, but it has its limitations for how we think about and manage water, and I think your point you're making, it devalues the importance of certain things like the water needed to get rid of salts in an irrigated system.
From the China example and going back to India example, it seems that the focus has been on agriculture as being the culprit. What about industries?
It's a great question. It goes back to the stat that I said at the beginning, that 90% of consumptive water use around the world is for agriculture and for irrigation. So there are probably localized examples where industries, and the Coke one could be one, are causing significant groundwater depletion. But the main story really is agriculture.
Because the way I understand it, with going by how the water movements are in India, I agree you'd say that you'd say that 90% of groundwater is definitely used for agriculture. And I pretty much also agree with the map that you showed about wells. But a farmer is really not consuming as much as industries are. The whole Coca-Cola example was huge. And also when you're talking about mining in those places in central India and all, it's just like large chunks. So what's happening right now is that also when it comes to dams, you have canals being built by the government, by the benevolent governments, and those canals are not maintained. And it was in a way to counter the whole groundwater usage. So the whole, the whole industrialized process has just been kind of negated by saying that just these farmers, because they do have small tracts of land, not everyone have like huge tracts of land.
Sure, yeah. Well, and it's I would never want to tell a farmer anywhere in the world, much less in a country that I don't live in, such as India, what to do with their farm. And you're right that it's not an individual farmer that's doing this. It's in a lot of ways it's a tragedy of the commons or a tragedy of common access, or easy access, however you want to describe the problem. It's the sum of many different farmers. Yeah.
Well, actually, I was trying to say that it's some of different farmers picking up, like imagine 10,000 ants picking up only as much as they can, versus one huge dog just picking up one big chunk of bread.
Right. And
that's what is happening with so many industries across all the countries that you showed on the map. That's what's happening. I mean, everywhere around.
I'm definitely not defending Coca-Cola or anything.
I think the point is that I think that's really, his perspective is very much a global perspective. And it's true that, I've seen estimates from 70 to 90% in most parts of the world agriculture is the predominant use, but if you look at certain countries, and particularly in certain regions, you might have whether or not it's industry using a lot of water or industry contaminating water, right? In the case of some of the examples you gave. So, these are topics that, it's a very valuable point, and it's a topic that in other kinds of study groups we cover, right?
But then I just saw like agriculture here as being the culprit, and I'm feeling that because that just cannot be the only one.
Yeah.
But it is true what he says that
I'm not denying that or negating it, but that is like a huge chunk.
Yeah, and it's a challenge too with all the standpoint of food security and how do you actually how do people maintain their life? It's a huge, complicated problem.
Yeah,
right?
for sure.
And I think what this work shows, which is really important, is that where plants are used in a basic productivity sense to grow and produce, they evapotranspire, but they pump water out of their leaves. It's consumptive use. And so how that actually plays out in a water balance sense at that scale versus a much more localised, potentially impact or contamination impact. And I think these are the important that's an important kind of message, because that's what we're looking for, isn't it, in terms of food security and productivity. It's how we most efficiently, evapotranspire through our agricultural systems and whatever, in the right place, in the right ways that's sustainable.
Yeah, how we maximize green water use. Yeah, that's a simple way of saying it. Yeah. All right, my time is ticking along. So
Yeah, we have about 15 minutes left of our seminar, so I feel like we've been interrupting you with questions, so we didn't really have but maybe we'll have a few minutes at the end for
sure.
additional questions.
For sure. I'll very quickly just talk about what I think the causes of groundwater depletion are. And when thinking about this problem, I've just really realized it depends who you are. And they're all right. That's actually my opinion. So hydrologists look at this problem and think, oh, there's just not enough recharge, or oh, there's too much discharge, or they think of it just as a hydrologic budget. I hear this at the meetings I go to all the time. So we have to increase the efficiency, or have to do this or that. And then you go and talk to an economist or something like this, and he says, well, this is a common pool problem, or it's how we value water. And that's really the cause of groundwater depletion. And then you come to the Harvard Kennedy School of Governance, and you hopefully talk to a bunch of policy people. And it's very clear also that there's not strong enough policy around groundwater in a number of different regions around the world. And my fundamental feeling is that they're all right. There's not a single cause, and we have to all talk together. That's why I'm happy to be here, in order to form a common language and common solutions and ideas. So I want to end with my David Suzuki. I hope everyone knows him. He's a famous Canadian environmentalist. And some ideas for the future solutions. The first idea is, I call these courses of action, is to set long-term goals. As I mentioned before, groundwater has very long residence times, and so you can make rational decisions about groundwater over 5 to 10 year spans, which very rapidly become irrational over multi-generational timescales. And you can think of this as a tragedy commons type problem. One of the ways to approach that problem is to set goals over a multi-generational timescale, so over 50 or 100 years. And then what's called backcasting, so that's looking from the future back to the present and determining what policy or management plans you need to do over the next 5 to 10 year horizon, which is really what humans in our current political system think, the timescale that we think over, in order to meet that long-term goal. So it's not setting a path for 100 years, it's just setting a goal 100 years in the future and thinking what we have to do on that short timescale to get there. I think of this as a very optimistic, very beautiful idea. And you can always change the path as you go, in like an adaptive management framework. This is actually being done in Texas. They're running groundwater models over 50 years to predict what different management scenarios over the next 5 to 10 years and how that will impact their goals for groundwater sustainability over the 50-year time horizon.
Well, I have to just interrupt and say, well, Texas is a crazy example because the Supreme Court of Texas ruled that basically if you think well, you can take as much water as you want out, sort of the prior appropriation rule, and it's legit. So, you sort of have a legal system that is going to be at odds with whatever sustainable framework you have in place.
I've actually talked to the people in charge of these goal-setting frameworks in Texas, and they're likely going to implode because of that Supreme Court judgment. Because the unfortunate thing is there's all these groundwater districts in Texas, and they have no funding, no source of funding. They're run by volunteers, and they have these amazingly progressive ideas about groundwater management, but now they're going to be sued by individuals for developing those management plans. So there's
I'm sorry to be pessimistic.
no, there's a
You're
yin,
optimistic.
there's a yin yang of everything. Another really another course of action is been talked about a lot for a long time by a lot of people, but integrative, adaptive, inclusive local management. This is just one example from India. That's a really neat project in Andhra Pradesh by FAO, where farmers collect water information about their watershed, about their aquifers, the water levels, the rain, develop water budgets every year and allocate water within their watershed, and have the graphic here is where in an open community setting where that water data is shown. So data is power, and this is a really cool example of sharing that data and distributing that power. I think that we need to start to value groundwater differently in many places of the world. I didn't have time today to talk about strong sustainability, but I've advocated that elsewhere. And this is shifting from just trading groundwater as a commodity and contaminating or depleting it, setting it aside in some areas using strong sustainability principles. And this would inherently be a different valuation of groundwater. And this is more of a hydrologist perspective, but has specific policy outcomes. Of the hydrologic perspective would be to decrease net groundwater use. So this is the difference between what we extract and what we recycle. So in an irrigation context, this would be how much we pump out versus how much is excess water is recharging the aquifer from that irrigation. And this can be done in a variety of different ways. From increased efficiency in rain-fed agriculture and artificial recharge, which is something I didn't get to talk about today. And the other part of this is we actually may have to protect natural recharge areas. And this is being done in some areas. Radical ideas in this area is like creating national water parks where we actually are developing protected areas to protect recharge in some very important regions. And I just wanted to end with this take-home message that groundwater is a large, valuable resource that is beneath our feet almost everywhere around the world. And it's critical for irrigation. And even though it's being depleted in a number of regions, we can start to shift towards more sustainable use.
Great.
Thank you.
Thank you. So maybe a few questions, especially from folks that weren't peppering him as he went along.
Yeah.
Thank you. It was very interesting, really very interesting perspective on such a huge resource of water. But I have a question from international point of view. It's very difficult to set some negotiations and laws on surface waters if they are transboundary, and if we speak about transboundary aquifers, it should be much more difficult. How optimistic directions of solving this problem? You might imagine if we speak about tragedy of commons, not between farmers in one state, but between two states who very need this water.
Right.
And who can manipulate with data about how much water they use, much simpler than this.
Right. So I guess it's nice to ground that in an example, and one poignant one would be the aquifer that I talked about in northern India and Pakistan. And I don't know. I honestly, it's a really complicated issue. I guess I would just say that it is a real issue, and how to share data between antagonistic states and develop a common vision for a shared resource is a huge issue, and I hope that you can do something about it. The only other thing I'll say is that the groundwater footprint could be used at this more local scale as sort of sub-aquifer units to calculate how sustainable the use or overuse or abuse of the aquifer is locally. And that could be used as a visualization and a discussion tool.
My question is more from the policy perspective, because I've been UNFO representative in China for over 7 years, and we work very closely with the government there. Hot button issue is food security. So they have to feed 1.3 billion people on a mere 7% of the world's arable land. It's a huge challenge. And what is happening is that there is so much water stress coming up in the north, and the desertification is increasing. And certain areas where irrigated, there's more water logging and salinity coming up.
Yeah.
So, it's a huge challenge. So what I did, I worked with the Israeli government. We had a huge project for Gansu project for dry land irrigation. How to use less water to increase productivity, bring in better seeds and high quality seeds, and so more intensification. So I believe that China, again, on the policy side, is following a very wise policy in that sense that they are on the one hand conserving water. Besides, even rainwater is being harvested in places where they just conserve it and use it when when there is less water available. So that's not a question, just an observation.
Yeah, no, it's there's a number of countries that are kind of microcosms of have almost all the problems all in one. And China is definitely one
But
of
they're
them.
raising more emphasis on productivity rather than increasing
Yeah.
production.
Yeah.
So that less land is used for.
I think you had one question over here.
I don't know if you know much about fracking, but it just seems I worry about it because I have this image that it shoots a lot of groundwater very, very deep. And you always say, you always learn that you don't lose water, it evaporates, it transpires, and it ends up back in the system. There's as much water as there was when it started, but are you putting that water out of reach? Are you subtracting from the amount of accessible water with fracking, or is it a significant quantity? Maybe it's not that much water.
It depends. Most water that's actually being used in fracking right now is surface water. There are some regions that are using groundwater. My main concerns around fracking are actually more water quality than quantity. I think it's really a contamination issue, and I do have another parallel study, or different study, I guess I should say, that is looking at the potential for hydrofracking to contaminate shallow aquifers. Because I think that's, in my eyes, that's the bigger issue than water usage, especially over the long term. Yeah, because a lot of so they have what's called flow back as well. So a lot of the water that's pumped down there and used to fracture the shale does flow back, but unfortunately it's contaminated when it flows back with both the stuff that's injected into the frack water and all the natural contaminants in shale.
Great. Well, please join me in thanking Tom for an excellent presentation today.